Hello and welcome to the 11th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we want to talk about segmentation using convolutional neural networks. But before we start, let's have a look at what happened in the last lecture. In the last lecture we talked about object detection using CNNs. And here we discussed basically two-stage approaches but also single-stage approaches. And here we discussed different approaches for achieving object detection, and we saw that the single-stage approaches reached now the performance of earlier two-stage approaches, and by doing this in also with anchor-free and anchor-based approaches. So the anchor-based approaches used basically templates to determine bounding boxes, and these templates were then refined and classified to get then the desired output for the different classes. In the anchor-free approaches, there we discussed the center net but also the corner net, used key points to determine bounding boxes. So this was a very interesting idea to determine the bounding boxes by specific key points which resolve to the center of the bounding box and the size of the bounding box, but also then on the corners of the bounding boxes. And for this we discussed different approaches with different architectures and different backbones and different ideas like the feature pyramid networks, which also will now play a role for semantic segmentation. So, but coming back to the perception task, so until now we discussed how to use convolutional networks for the classification, and we covered in the last lecture the object detection, where the task was to localize objects. And now in this lecture we want to talk about basically the remaining perception task, or the main perception task that we're interested in, and this is the so-called semantic segmentation, where we want to provide for each pixel of the image a semantic label, but also the panoptic segmentation. So, but to recap the semantic segmentation, here we have as input an image, and using a convolutional network, we want now to output basically for each pixel location a different class. So in this case, for instance, here we have the road surface classified by the purple color, so we are classifying these pixels as road. Then we have the cars classified by these blue pixels, that are cars. Then we have the bus and the building surfaces classified. So that means this is a more fine-grained classification than an image classification, where we really want to have for each pixel a different classification output. But coming back to the image classification, so the usual approach was there to use a convolutional network with pooling operations or strided convolutions in between to reduce the resolution. And then in the end we want to have classification vector out of size k, where k is the number of classes. So these are then our class scores. And in the semantic segmentation we now want to produce the same, but the class scores should now be for each pixel of the image basically. So that means we are not getting only k class scores back, but we are getting for each pixel in the output image basically an class score. So that means we can now use something like a pixel-wise cross-entropy loss to steer the learning of the convolutional network. But so the thing that we have to now do basically is to get from the reduced feature map size back to the pixel-wise classification scores in the end. And for this one has to account for when we are doing the reduction via strided convolutions or via max pooling, we are basically reducing the feature map size from in each state basically by 2. So that means we are starting with h by w in the beginning, but then after each pooling operation or strided convolution we are reducing the size by 2. So that means in the end we are reaching something like the image size divided by 32, for instance. And then we have to do, of course, something to regain the size in the end. because we not only want for the small feature map basically the classification scores, but in the end we want to have for each pixel the classification scores. And for this, the so-called fully convolutional neural network proposed to do then this upsampling in the end. So in the end, we are doing again the same as we had with the image classification. We have our normal backbone of convolutions with reducing the feature map size in between with strided convolutions or max pooling operations. And then we are doing an upsampling such that we are reaching then the original image size in the end. And the specific part that now was done in the fully convolutional neural network was the to use a one-by-one convolution instead of the fully connected layer in the end. So this last part is basically then replaced by a convolution, so therefore it's also called a fully convolutional network in the end. And for upsampling, the FCN now made the following. So in the base case, the feature map that came out, which is then a 32-dimensional, 32-strided output feature map, is then just upsampled to the original size. But as you can see, by using this upsampling, we are basically getting only this blobby prediction spec for the class predictions in the end. And the FCN now proposed different ways to get more fine-grained results in the end by then doing also taking into account the feature maps from earlier layers, and then by doing there the upsampling and the convolutions in the end, and then upsampling only the convolutions 2 times, and then combining this with the features from the earlier pooling layers or from the downsampled feature maps, and then doing only an upsampling with much smaller upsampling rates, so like 16 or 8 times upsampling. And as you can see in the results, then the predicted output maps of the labels that we get are getting much more fine-grained in the end. So what these works basically showed is that the upsampling operations that we are using is basically determining how well we are doing maybe the semantic segmentation in the end. And instead of doing this upsampling in this way, we can also think of a different way. So we talked already about the encoder-decoder architecture. And the encoder-decoder architecture is here the normal convolutional neural network with, here in this case, strided convolutions in between, which gives us then the feature map for this image. And then we can use basically a mirrored representation as a decoder where we have the upsampling operations in between. And this has the advantage that we are not directly upsampling to the original image size in the end, but have some convolutions in between which can then produce more fine-grained predictions in the end. And by doing this, we're getting then a higher spatial resolution in the end of the predicted semantic segmentation mask. And the UNet architecture now brought in to also use some skip connections in between. So because the usual learning with this encoder-decoder architecture is not retaining the high resolution information in the decoder again. So, and for this, the UNet architecture proposed to also use the feature maps from the encoder and combine this with the feature maps from the decoder. And this worked as follows. So we have our upsampling operation, which is a transpose convolution or bilinear interpolation. So we talked about this in the object detection lecture. And by then we're upsampling, so the size of the feature maps is then increased. And then we are using the feature maps from the encoder and combine them together with the upsampled feature map, so by a concatenation in this case, and then use again a convolution to reduce then the number of channels again to the desired number of channels that we want to have in the end. And by using this strategy, we can then get much more fine-grained results in the end. And this skip connection idea was then also followed by other approaches. And in this case, from SegNet, we have again our encoder-decoder architecture. But now the skip connections are not taking basically the feature maps from the encoder into account, but use the max pooling indices, so which are happening here. So there are max pooling layers in between, and using this indices to then do the unpooling basically. So this is a different way of upsampling the feature maps in the end. By using this idea, they can also get then a better upsampling in the end. And this idea of taking into account the, for each pixel, we want to have basically the contextual information around this pixel. And for getting a larger receptive field in the end, what we want to have to distinguish different pixels for different regions, we want to see the, as much as possible from the image to decide what this single pixel belongs to. And in the case of the so-called pyramid scene parsing network, this was achieved by using on the final feature map different pooling operations that gives us then a reduced feature maps in the end. But on top of this, then we can apply convolutions, and as the convolution is now taking these pooled features into account, it can basically see much more of the original feature map in the end. So this downsampled version here can now see a larger part basically of the outcome feature map of the CNN in the case. And then what happened then, we upsample this downsampled feature maps again and then combine it via skip connection with the original feature map. And by using this, then with an additional convolution in the end, we're getting then the semantic segmentation classification scores for each pixel in the end. And the larger receptive field is something that we want to have basically always in the CNNs. And this is usually achieved by using pooling operation or strided convolutions. And just to remind you how this influences the region that can be seen from the original image. So that's basically the idea. So for when we now apply the convolution, or when we apply the convolution to get the feature map, we are basically applying this on this original image like this. And when we now have the max pooling operation, then the convolution that produced this feature map output is basically then taking into account a larger convolution from a larger field of view from the previous feature map, and this corresponds then of course to a larger field of view in original feature maps. So, and by doing this in between with the multiple max pooling or strided convolutions, we are basically then at each layer seeing more from the original image in this case. Because each 3x3 convolution is then taking these values into account, which were produced basically by these values, and this were produced by this initial image values. So this is something that we want to have basically in the end. But this comes with a downside in the end, is by when we are now looking at neighboring entries in the feature maps, then these correspond to different spatial locations in the original image, so to say. And when we have the initial convolutions applied, and so the outcomes of this are basically then applied convolutions on the original image like this. But when we are then going down, then neighboring entries from this feature map are then represented by the strided points here in the original image. So when we are now striding here over this feature map, we are basically making larger jumps in the original image, so to say. And this, of course, the deeper we get in the network, the larger this jumps basically in the spatial resolution happen. So, and this is one downside of using the strided convolutions in the end. And this is something that we don't want to have when we have semantic segmentation. We basically want to have very fine-grained information for each pixel, so we want to slide the convolutions in very fine-grained way. So, and these can be solved by using the upsampling in the decoder, where we then applying the convolutions on upsampled feature maps, and therefore we are doing the application of the convolutions then in a much denser way. And a different way to solve this is basically proposed by the so-called deep lab approach. In the deep lab approach, there's this dilated convolutions introduced, or truth convolutions. Here the idea was, when you remember it from the lecture where we talked about different ways of doing convolution, there was also the dilated convolution. And in the dilated convolutions, the kernel elements are spread out a bit. But this comes on the next slide, will also be a little bit more explained. And here we have our CNN backbone that produces the feature map. Then we're applying this ASPP module on top of this, and then we have a decoder which then uses these features, so from our backbone, but also our ASPP features, and then produce in the end the prediction that we want to have. And for the backbone, we can now also include this dilated convolutions to basically achieve the same thing as we do by downsampling in the end. So by using the dilated convolutions, we also want to have a large receptive field, and this is then achieved by these blocks here. So here in the beginning, we have the normal downsampling with max pooling or strided convolutions, and by each max pooling or pooling operations, we are increasing the output stride. So from 4 to 8 to 16. So output stride means how large is the stride in relation to the original image in the end. And what is now done here in this case is that we then apply in the lower layers not any more pooling operations, but use different kinds of dilated convolutions. And by using this, we are then keeping the output stride the same, so the feature maps are not halved in size again, and but we apply the dilated convolutions with different rates, which achieve basically the same as by doing pooling operations. With this, we are getting also a larger receptive field. So for producing block 7, we are then using the dilated convolutions in this way, and then we are getting also the same benefit of having a larger receptive field. And this idea is then also taken into the ASPP module, which is very similar to the PSPNet, but in the PSPNet we had different convolutions which worked on different pooled feature maps. And in this case, we have the similar idea, but have the same feature map, but apply different dilated convolutions here. So with different spacings between the kernel elements in the end. So we have then 1x1 convolutions, then a dilated convolution with rate 6. So the elements of the kernels are basically 6 pixels apart, and then we are increasing this, concatenating this, and then doing usual 1x1 convolutions to reduce the channel number basically to the desired channel number, and then we can use this feature again. And the same idea as in the PSPNet was like to, by using this block of different dilation rates, we can basically capture here different contextual sizes, like in the feature pyramids networks or these image pyramids in the end. So by using the dilated convolutions, we are basically getting different scales into account here. And with this, we are then getting a feature that can capture better the contextual information of the feature map in the end. And by using this, we are then getting, in the end, better results. To attain this high resolution application of the features, there was also a different way proposed, in the high-resolution network. And here the idea was to have different branches with different sized feature maps, which are then mixed together. So we have here in the stage 1 the normal convolutions applied, and then in stage 2 we are applying not only the convolutions on the downsampled feature maps but also on the feature maps in the same size, and then we are mixing this together. So arrows that go down is basically a downsampling operation, and when the arrows go up, it's basically an upsampling operation. And as you can see, in each stage we are getting more branches, which are then having also larger receptive fields, basically on the feature maps of the previous stage. But we are also retaining this high resolution branch, basically, where we are not reducing the feature map size. And in the end, we are concatenating this together to get then the desired output of our feature map, which we then can use to do the classification, pixel-wise classification in the end. And the downsampling was here done by strided convolutions, so these arrows that go down are strided convolutions, and the upsampling were simply bilinear interpolations, which has the advantage that we are not using extra parameters in the upsampling part. We now discuss different ways how to aggregate information for doing then the semantic segmentation in the end. And the question is now, how do we actually evaluate the semantic segmentation? And for this, the common metric is basically the mean intersection over union. And as in the detection part, where we had the intersection over union of two bounding boxes, this is similarly defined now for the segments. So, but here we are taking into account the pixel-wise assignments. So here is shown one region, that is the ground truth region, and then we have the prediction that is maybe a little bit different. And then we have the overlapping regions, this is the true positives. So this is this part in green here. So there the pixels of the ground truth and the prediction have basically the same class. So these are our true positives, basically. And then we have the false positives, where our prediction says this is maybe car, but it's actually not car. For this, we are then having the false positive pixels. And then we have regions where our predictions doesn't say that this is a specific class. So we are then having here the false negative regions. And the intersection over union is then in a pixel-wise way defined as the number of pixels which are true positives divided by the true positives plus false positives plus false negatives. And this is, of course, then the same as in the bounding box case. So the true positives is basically the intersection of both regions, and this part is then the union. So this part in between, and then the other parts plus this. And now we have defined this basically for a single class. And for the whole image, for different classes, we are then taking just the mean of the class-wise intersection over union. So that means here we are dividing the sum over the intersection class-wise intersection over unions by the number of classes. And this is then the metric that we are interested in. And this is then, of course, also then applied to different data sets and common data sets for doing semantic segmentation, but also panoptic segmentation or instance segmentation. For instance, here the MS COCO data set, which features 80 different categories. So as I already explained in the lecture on object detections, there we have instance annotation for 80 classes, featuring images from the internet like Flickr or Pinterest or something like this. So they were just taken from smartphones or cameras or something like this. And then they were annotated densely with instance segmentation mask like this here. And there are over 118,000 images in this data set. And they are mainly used for panoptic segmentation, but also instance segmentation. A similar data set with a much larger number of categories is the so-called ADE20K data set, where we have over 2,600 different object classes. So it's very fine-grained annotated. But for the actual evaluation is then only 150 classes used, which are showing the most common objects here. This is also much smaller because of this finer annotation, so it's something on the order of 25,000 images, and mainly used for evaluating semantic segmentation, but also instance segmentation. These are data sets basically captured with normal smartphones or that you can find basically also in your Facebook stream or something like this. But the difference here for the cityscapes and the MLRCV vistas data sets, these are more targeted at autonomous driving in the end. So the cityscapes data set specifically is captured with a camera that was mounted on a normal car. And the cityscapes data set has cities of different cities from Germany, and these images were then captured and annotated. And here, this is specifically here now a scene from Bonn, and this shows then only 30 classes, from which 19 are used for evaluation, but it shows mainly classes that are relevant for autonomous driving, like the drivable space, like road, the non-drivable space, like sidewalks, but also pedestrians here in red, and other structures that are standing around there and might relevant for autonomous driving. And the MLRCV vistas data set shows a much larger variety of images, also from different geographic regions. And these images are not necessarily only captured with cameras that are mounted on a car, but it can also maybe feature street scenes that are captured just with a smartphone. So it's a variety of different images that are not only captured from an autonomous vehicle maybe. But for this, then there are more than 66 categories available, but also the same number of size so as the ADK data set. And this is then also used sometimes for semantic and instance segmentation evaluation. When we now look at our different approaches, here I gathered some results from the papers. So for the ADE20K validation set, we have here a segnet which reaches already 21% mean intersection over union, and then we have the more advanced approaches which use much more contextual information, like the PSP-net or the high resolution network. Then we are reaching something like 40+% mean intersection over union, and more targeted at the autonomous driving space, the evaluation on the cityscapes data set. And here we have the Deep Lab version 3, which already reaches over 80% intersection over union. But here you have to remember that these are evaluated over 19 classes, and these are a much larger size of larger number of classes in the end. But you can also see here, maybe in the results from the PSP-net, that you still have problems with fine-grained results. So some parts are just missed in the semantic segmentation because they are very, very small. So therefore, approaches like HRNet are improving on this, and there are also other developments which try to get then also these classes right, which are very fine-grained in the end. We now talked a lot about the semantic segmentation, and one intermediate step to then come to the so-called panoptic segmentation is then, of course, how to segment instances. So in difference to the semantic segmentation, where we are assigning all cars basically pixel-wise the same label, we are interested now in instance segmentation in distinguishing different cars. So that here the colors indicate different instances of the car, so that we really can now maybe also count how many cars are in the image. And for this, we are coming back basically to the object detection. for doing instance segmentation. So this was one of the first successful approaches that showed that we can also do very good instance segmentation in the end, and this was the so-called mask RCNN. So this part you already know. So you have an image, you produce with a region proposal network the proposals, which are then classified by classification and bounding box regression head. This is the first part. This is just the detection. And then what mask RCNN added was basically a part where we have not only for the region of interest a class and a refined bounding box, but also for this region of interest and fine-grained instance segmentation. So we are then saying basically for each bounding box, for each pixel in the bounding box, which are the foreground and background pixels. So there's additionally the distinction between foreground and background pixels for each region of interest. And in particular for the mask RCNN, the authors proposed a different pooling strategy. So as you might remember from the lecture, so we have our input image, we have our anchor that is produced by the region proposal network, and now to extract in this faster RCNN structure the features for doing the classification of the bounding boxes, we are now just taking the bounding box, discretizing this, and getting then the corresponding part of the feature map. And for the discretization, so when we maybe have here an output stride of 32, we are just dividing the high resolution bounding box pixels by 32. And then we are doing some discretization operation like rounding or the floor operation, and then we are getting basically some part of the feature map that corresponds then to a different part than we are basically interested in. And this is not so bad for the classification or for the regression, but for the authors of the mask RCNN paper found that this is not a desired property that we want to have when we want to have really fine-grained instance segmentation masks. So the region of interest pooling had to be adapted in this way. And for this, they propose to use for each cell of the output region of interest feature map a bilinear interpolation. So for each cell, we are then using 4 places where we do a bilinear interpolation of the feature map entries, and then we're accumulating there the feature distribution here in this bilinear interpolation way, such that we are getting then the precise location of this feature and the precise location of the bounding box in the end. And with this, we again can get very good instance segmentation masks. So the mask RCNN is basically, for instance segmentation, one of the main workhorses that are used for instance segmentation. So a different way to do instance segmentation was basically then proposed by a different group, where we come back to the similar way as we did with the center net or the corner net in the end, where we have basically for each pixel an embedding vector we want to estimate. And the idea is here that for different instances, we are producing embedding vectors for each pixel, such that the embedding vectors of pixels that belong to the same instance have a smaller distance than embedding vectors of different instances, as shown here. So 2 different pixels of the same instance produce embedding vectors that are very close together, while embedding vectors of different instances should lie farther away. And then by using this, when we are then producing the embedding vectors, we can use clustering to determine basically all pixels from different instances. And for doing this, we can now not only produce embedding vectors for a specific class, but we can also do this for multiple classes. And here the idea is to use one encoder on the input image, and the encoder here in this case is again with strided convolutions in between. And then we have 2 decoders, one decoder that produce the embedding vectors in the end, and then one decoder that produces our semantic segmentation. And then both together, so the semantic segmentation and the embedding vectors can then be used to cluster the instances of a specific class. And for the embedding loss, we are using then the same idea as we had with the center net. We have here then over all our classes, over all our instances, or over all pixels from this specific class. We want to have that all the embedding vectors xi are close to the mean of the instance. And here in this case, we want to have it in a way that the distances of the individual pixel embedding vectors are below a certain distance here. And for this, they use this hinge loss in this case, so such that as long as the distance from this individual vectors to the mean is smaller than the delta v, we don't care exactly where the embedding vectors lie. So we don't want to necessarily drive them to 0, but we want to have them that they are below delta v. So this is this term taken care of. And for different instances, we want to push basically the instance vectors apart from each other, and for this we are just inverting basically the distance here. So we want to have the distance such that it's larger than delta d in the end. So by subtracting the distance between the mean vectors, as we had this for the corner net, we are then getting the embedding vectors such that for the same instances, they are close together, and for different instances, they are pushed apart. And in this case, in this work from Brabandere, we also did they also did this for the classification. So therefore, you see here the C inter in there, but this can also be done for the instance segmentation. And another part that was then added to the loss is basically a regularization, so that we are not getting the embedding vectors spread over the whole space, but we want to have them that they are close to the center, so to say, so that we get in the end bounded embedding vectors, so to say. And by doing this, then we can then infer embedding vectors for each pixel, such that the embedding vectors of hopefully of the same instance are close together. And then for the instance clustering, we then can use something like mean shift, and in this case, a variant of the mean shift vector. And as you remember, the distance of the same instance should be smaller, or should be learned in a way that it's smaller than delta v. And then for doing the clustering, we can then use the following procedure. So we select one pixel that is not assigned to a specific class or a specific instance in this case, and then we set the mean basically to this specific embedding vector. Then we get all pixels that belong or are closer than this delta v distance, and then from all these pixels we are computing a new mean. So this is very similar to the k-means approach, where we have this ping-ponging between figuring out which points belong to a certain cluster, and then updating the cluster center, and then doing this again. So that means here in the last step, we are recomputing the mean, and then we are getting back to step 2, where we are determining all pixels that are closer than delta v to the mean, and then we are assigning this to the specific cluster. And then by using this procedure, we are iterating this until the mean doesn't change anymore. And then we have basically found one instance, and then we are doing this the same for the other instances or classes in the end. And we have now discussed 2 basic approaches basically to do instance segmentation. And the first approach was basically a top-down approach, where we already know where certain instances are located. So these are given by the boundary boxes or by the anchors, which locate objects or possible objects. and then we are just refining this by predicting a foreground mask for the specific instance. So we don't have to care about different instances, we just have to find the instance that is belonging into the bounding box here. So this is the so-called top-down approach. And in the other case, where we are using the embedding vector, we're having basically a bottom-up approach. So we are predicting for each pixel a property, and then using this property to cluster the instances back together. So this is then usually called a bottom-up approach. And these are the two paradigms that we also now will encounter when we are talking about panoptic segmentation, which is the next part. Just as a reminder, in the panoptic segmentation, we are interested not only in the semantic labels of each pixel, but we also want for specific classes the instance annotation in the end, so that we can distinguish in the end the different cars. And this corresponds to, in the panoptic segmentation, to this distinction between stuff and things. So stuff is something like vegetation, road, or also buildings, where we not clearly can distinguish maybe different objects in the end. And the so-called thing classes are then objects where we can clearly say, okay, these are different cars, or these are different pedestrians, and this is the distinction. So we have a specific part that is corresponding to stuff, and we have a specific part of the class that correspond to thing classes. And for the stuff, we are basically interested only in the semantic segmentation. So we are assigning all pixels basically the same instance in the end. And for the thing classes, we want to also distinguish between different instances. And one of the first approaches to do panoptic segmentation was the so-called panoptic FPN. So here a feature pyramid network was used, which is very similar to the approach with the encoder and decoder. We have the backbone network that produces our feature maps with pooling operations or strided convolutions in between. And then we are aggregating this to get the feature pyramid in the end. And then we have two branches. One branch is just the normal way of doing the instance segmentation in the mask RCNN approach. So we are producing with a region proposal network bounding boxes or anchors, and then using these anchors to refine then the bounding boxes and classify them, and then also produce the instance segmentation for these bounding boxes. And then on top of this, since we are now doing panoptic segmentation, we are interested also in the semantic segmentation of the stuff classes. And for this, then there's the segmentation branch. And for the semantic segmentation branch, the authors also use the feature pyramid network. And here they aggregated them together via upsampling and then some convolutions in between. And the concatenation gives us then the pixel-wise class scores that then can be used for determining semantic segmentation. And in this case, they included for the semantic segmentation part, because we have now this distinction between thing and stuff, they included also a capture class that combines basically all thing objects together, which is then also predicted by the semantic segmentation branch, and then they can combine both together then to get the desired panoptic segmentation in the end. In the same way, this top-down approach, so this is the top-down instance segmentation, there were also other approaches proposed at the same time. Concurrently, basically, we have here this seamless segmentation, which is using a very similar strategy of having one feature, one shared encoder. This is the so-called body in this case. And then we have this region proposal network that provides us with proposals from anchors that we can then use with the Roy align strategy to get then the mask predictions for the detection bounding boxes, which then leads us to the detections. And then we have a different branch which provides us then with the semantic segmentation, and then again we have some fusion between the provided instances from the detection and the semantic segmentation to give us then the panoptic segmentation. Very similar to the panoptic feature pyramid network was this unified panoptic segmentation, or UPS net, which also used the feature pyramid networks and then two different semantic heads or instance segmentation heads. And as you can see here, this is very similar to the mask RCNN approach, where we have also a classification of the region proposals and the different objects, and then the mask logits, which are basically just the foreground background distinction for this mask to give us then the instances. And then we have here the semantic segmentation part, which is then combined with an additional network or additional layers basically into a panoptic segmentation in the end. And these are top-down approaches, so to say, to tackle the the panoptic segmentation in the end. And there was also a bottom-up approach, which is the so-called panoptic deep lab. As you can see here, we have the shared encoder again, and then the ASPP parts, which we know already from the semantic segmentation with deep lab version 3+. And then we have a semantic branch, which is very similar to the way that Deep Lab did the semantic segmentation, and this gives us then the semantic segmentations. And then we have one instance branch, which provides us then with a bottom-up approach to determine the instances. And here we have centers and the center offsets, and then both are grouped and combined to get then the panoptic segmentation. And for the instance part, there was a particular idea to do the instance segmentation. Here the approach was to first determine centers for the objects. So we had one center regression part, which is very similar to the CenterNet approach. So for each of the thing classes, we want to determine the center location of the objects. And with this, we are then getting basically the location of the objects. And then we have also, in this case, we also produce for each pixel in the image an offset location. So which tells us where should be the center of the object. So these are the center offset locations. And for getting then the desired clustering, we can then use the semantic segmentation to determine which class these instances have. And for getting the instances, we can then use the offset vectors that are pointing towards the centers. And then when a center is located near to this location where the offset vectors point, we can then cluster the pixels together. So we are clustering basically all pixels together that are pointing at the same center location. And with this, we can then assign instance IDs in the end. Now, as with the semantic segmentation, we also have to talk about how to actually evaluate then the quality of the panoptic segmentation. And for this was the panoptic quality proposed. And here we are not talking directly about pixel-wise association, but about segment-wise associations. And here the panoptic quality is determined for each individual class first. So we have first a class-wise segment assignment. And here on the left is the ground truth shown of the simple scene where we have stuff classes like sky and grass, but also thing classes like person and a dog. And in this case, we have our predictions, which are now providing us with segmentation masks of the, or instance masks of the thing classes like persons. And now we have to match these segments together. And for matching the segments, we are always looking at a ground truth segment, and we are looking at the intersection of a union with a predicted segment. And for the true positive matches, we basically want to find all segments from the predictions with the ground truths that have an intersection of a union larger than 0.5. So in this case, this would be these both segments that have an intersection of a union over 50%, and the Person segment from the prediction with this Person segment from the ground truth has also a larger intersection of a union. So this is then our set of true positives. And then we have unmatched predictions, which in this case our false positive. So we have a prediction here of person, which cannot be matched to another person segment in the ground truth, because this is classified here, or this should be a dog, and we are classifying this as person. So therefore this is a false positive. And then we have unmatched ground truth segments, which is in this case this person segment here, which is then the false negative. So for this we don't have any predictions that are having a larger overlap than 0.5. And from this, we can then, from the segment assignment, we then can compute the class-wise panoptic quality, which is then the sum over the intersection of a union between the true positive associations and divided by the number of true positive associations plus 1/2 of the false positives and false negatives. And this gives us then the class-wise panoptic quality. And as in the case with the mean intersection over union, we have now basically the mean panoptic quality, so to say, which is then the overall panoptic quality PQ is then given by the mean over the class-wise panoptic qualities. In the case of the panoptic quality, the authors of the seamless scene segmentation part came up with some shortcoming of the normal panoptic quality, which is maybe over penalizing the stuff regions in the end. So because in this case, when we have here, for instance, this ground truth, and we're making small errors in the segmentation of the stuff region, like this sidewalk here, which is a stuff region, when we then compare the intersection of a union between these two parts here, then this is maybe below 0.5. So this would be then, even though it's not that wrong, it will still be counted as a false negative or a false positive in this case. And therefore, the authors of the seamless scene segmentation paper propose to do for the use only the class-wise panoptic quality basically for the thing classes, and use for these just the intersection over union for the stuff classes. And this is then as follows here, like we are associating all segments from the stuff class which have a larger than intersection over union than 0. So in this case, this would be associated with the sidewalk here. And then we are computing the intersection over union between these two segments and divided by the number of the ground truth size. And then by using this, then we are getting a much better panoptic quality in the end that we can then also use to fairly account for the semantic segmentation of stuff in the end. When we are now talking about results, so here are some results from the so-called cityscapes data set. Here is the panoptic segmentation of the seamless segmentation, and in comparison to the panoptic feature pyramid networks. And here you can see the development over time, so to say. When we have the panoptic feature pyramid networks, we are reaching something like 58% panoptic quality, and what you usually see in the papers is also a distinction between the panoptic quality for the thing classes versus the panoptic quality of the stuff classes. And then on top of this, also the semantic segmentation quality when we are not accounting for instances, then given by the mean intersection over union. And yes, you can see this bottom-up approach with the panoptic deep lab is then reaching something like 62% panoptic quality in the end. Just to give you an idea how well or how far the approach is reached already on the cityscapes dataset. And with this, I'm already at the end. So in this lecture, we discussed more fine-grained scene understanding, where we want to produce pixel-wise instance segmentation masks, but also semantic segmentation masks, which then ends also in the so-called panoptic segmentation, which basically unifies both of this. So the semantic segmentation, but also instance segmentation into one single output, so to say. And this is also something that might be relevant for autonomous driving, because it gives you an idea about where are its drivable surface and where are individual objects that you are caring about, like individual cars here in this case. For all these tasks, we discussed different common and popular approaches, so that you also can now go into the papers and look for more details, but also have a good overview over the related work in these areas. So thank you for your attention, and then see you next week.